we'll move on to our discussion session.
All right, so we know that we are the last thing between you and lunch, so we're going to keep this brief and lively. We've come up with some sort of wordy, long-winded questions, sorry, but we think they're good questions and we need words to explain them. So we'll see how many we get through. Well, let's just start at the top. So here's a question that we had. Do the differences in the burstiness of star formation predicted by different simulations, is that going to lead to different predictions in the amount of feedback, stellar-driven feedback? I would assume so. When I look at the fire simulations, it looks like you have pretty extreme-looking stellar-driven feedback. I don't see that visually as much in the other, but I wanted to know how much agreement is there among simulators on, like, we've heard a lot about differences in burstiness. We haven't heard as much about differences in stellar, like the importance of stellar feedback. And then what are, assuming that there are, what are the observables that can constrain these different predictions from simulations regarding stellar feedback? We'll open it up.
Hi, thanks. With regard to the observables that can constrain the difference, I mean, certainly what seems to be becoming more and more popular over the last, 5 years or so is looking at properties of the circumgalactic medium to constrain the different modes of feedback. I think it's pretty safe to say that using properties of the galaxy itself, in particular the stellar properties of the galaxy itself, to constrain feedback models doesn't really work, because they all give the same answer for different reasons.
I agree with what Nir just said, and I wanted to point out that we did a test that I think sort of focuses in on this in the Agora project, the so-called Cosmo Run, and it's the 6th of those papers, the one that Clayton Strawn led, that looked at the circumgalactic media. So this is 8 different runs with the same initial conditions of a Milky Way mass galaxy, and some of them, and the only physical difference besides the difference in the way that the calculations are actually done, was the feedback. So they had a variety of different feedbacks, and that had a tremendous effect on the circumgalactic medium. Some with strong feedback filled the circumgalactic medium with enough ions to be consistent with observations. Many of them did not. So I think this is a point that you made yourself in your talk today, the first part of your talk today, Allison, that you need fairly strong feedback leading to these bursts of metal-rich gas out into the circumgalactic medium. And if you don't have that, you're not going to be consistent with the observations.
So I'd like to kind of comment on question 1, and maybe this is a question for the fire people specifically. But I was wondering whether, since the prediction is that the disks at these early times are just these chaotic messes, whether there are strong statements that they can make about what they absolutely must see in terms of the morphology of high-Z galaxies, axis ratios, Gini coefficients, these sorts of things. Like, is it actually possible with stuff we already have to falsify or confirm those sorts of predictions, just from morphology?
I'm not sure I can point to like a specific number to measure, but when you look at high redshift low mass galaxies, they are morphologically disturbed. There's evidence that they are at time variable star formation rate. So they look very much consistent with what I see in the simulation, at least at the first order level. So others might disagree, and that's why we're having a discussion. James.
I would just add, like, I agree with Claude Andre. I mean, qualitatively, it's not obvious, but I think what that means is that we really need to produce mock images. We have to go through the process of doing sort of mock images so that we can really compare in a one-to-one way in the parameter spaces that exist in the data. I mean, the data are there. We just need to actually produce those predictions. I think with the Firebox HR, we can definitely do that, start to do those things more carefully at higher redshift. With large number, you know, we suffer from the statistics issue, but Firebox helps with the statistics thing, for sure, I think.
Maybe also just like a general comment. I mean, the morphology is probably, you know, some of the hardest thing to do in the simulations. I mean, to do it right, let's say, right? So they're definitely. We had a discussion about convergence at some point, and that's probably one of the property that's least converged. So yeah, so one should keep this in mind.
What about the classic dark matter profiles question? I mean, for example, my understanding is TNG produces generally dark matter cusps, while many of these other simulations have cores, at least in a similar mass range. Is that not a relatively easy way at low redshift to tell the difference?
Yeah, sorry. I mean, I would say yes. I think so. I mean, you know, I still hear a lot of people saying they don't believe that these cores really exist in the real universe. But I think if they do, I mean, no one's done that in CDM simulations without some level of bursty star formation to drive it. And I think bursty is a little bit too simplified, but it has to be asymmetric and not spread out over the system. And you can start making these cores. And so if we really do believe they're there, it suggests star formation is something like that, or the dark matter's not cold, right? So then then you have to get into that, you know, it's SIDM or something like that.
With regard to burstiness, there are galaxies which are extremely compact, and they're blue. They explode they give like 200 times the energy needed to blow up the gas. I'm sure that there are velocity differences, and so I think using the simple word stellar-driven feedback, I think there are, depends on its location, in the middle, different. I think it's the next level of the question is, what kind of feedback are you talking about? Conventional feedback, so that the outer part of the disk is not forming versus the central part getting replenished. So I just wanted to say that there's more variety to this question.
Yeah, I want to follow the question Aaron and James discussed. So I think in observations we do see, as I just showed in my previous talk, there's the feature between basically the stellar feedback and kinematics, and also the morphologies. So I think stellar feedback is definitely there. I think the question is how much it contributes, or it's, you know, if it's the only, you know, way to produce dark matter cores, or other, like, you know, different dark matter mechanism can, you know, also contribute to you know, the core formation. So I think one other thing can test is, you know, the sizes. We talk about, you know, this with different people. So what's the size, like mass size distribution, you know, in this low mass, you know, dark matter core low mass halos or galaxies actually, and it seems to me that the mass size relation in those low mass galaxies are not well, you know, modeled in the Hydra sense. At least, you know, different Hydra sim give you different mass size relation, and it's also different from the observations. And I think that's something we can look into.
Let's go to the next question. It's your question. You want to read it?
All right, yeah. So my question was, well, you can read for yourself, but I was interested in, you know, we now think that, you know, starbursts are visually spectacular, but they're not how most stars form. Most stars form in a sort of relatively quiescent mode. The question is, how about most mass loss? We know that, you know, we have to lose most of the baryons, or we have to lose most of the metals from galaxies. Certainly true at Milky Way mass. You go to dwarfy things, we lose even more. To what extent does the mass loss pattern follow the star formation pattern, that is, starbursts are spectacular, but they only are, say, 10% of the mass loss? Or is it different? Is it the case that, you only form 10% of the stars in the starburst, but those 10% are responsible for all of the mass loss or all of the metal loss? How can we get at that question both from simulations and observations?
I've gotten into the bad habit of talking too much. I promise I'll stop. But it's a really interesting point. So immediately I go to the Milky Way, right? The Milky Way looks like it formed early. It's overly massive for its halo. So it's probably been forming in this non-bursty stage longer than most galaxies of its size. I don't know, is its metallicity or chemical properties different significantly than other galaxies of a similar stellar mass or halo mass? I don't know the answer to that, but that's an interesting data point because we know it's weird in a lot of ways.
You want to comment on that or anything else related to this?
I think it's a really good cutting edge question that everybody's like, we don't know. Everybody's just tired of it. I think it's a great question. Is this something that people have looked at in the simulations? Because in the simulations, you can just make plots, right?
So in fire, the answer to question number 2 is that most mass loss from galaxies occurs in the bursty phase. And the reason I can say this is by the time you form the nice thin steady disk, the outflows have basically died down and turned into galactic fountains.
Well, okay, so here's my question then. How do we reconcile that? I mean, most of the stellar mass forms not in the bursty phase, right? Most of the stellar mass forms late.
Yeah.
Right, so, but if you're not losing much mass then, I'm not quite sure how you reconcile that with the integrated constraint that you have to lose most of, right, that the baryon, you are well below the universal baryon fraction. So it seems to me like maybe you lose more during the bursty phase, but, if I said that no mass loss occurs from the Milky Way after redshift, after 10 billion years ago when it settled down, I would think we would wind up with way too many baryons in the Milky Way. Well, okay, but I mean mass loss from the disk. So is it just that, most mass loss is simply that it never gets into the disk at all, right? Is it basically the halo quenching picture that you don't have to eject much mass, it's just that most mass never gets to the disk in the first place?
I think there's a big part of that is happening, but if generally speaking, what like in these bursts of star formation that I asserted ejects most of the mass from the galaxies in fire, they not only eject mass in the galaxy, but they deplete halos of baryons at high redshift. And so by the time you have a 10 to 12 solar mass halo at redshift of 0, it only has half of its kind of baryon.
Right, but the point I'm making is that most of the accretion most of the mass that the halo is going to gain is in the quiescent phase, not the bursty phase.
But most of those baryons have never been in the galaxy, though. I think most of the stars are forming like in a large thin disk, but I think most of the baryons have never been in there. Like most of the baryons you see around the Milky Way, I think have not been in the Milky Way. I think.
Right. The point I'm trying to make is just that you need to have you need to have a way of having all of the mass that accretes after 10 billion years ago, which is most of it. You need a way of stopping most of that from going into the disk. And so if it's not feedback, then it has to be halo quenching or something like that.
Oh yeah. So by the time you have this large thin disk, you have a hot halo that takes a long time to cool.
Any other thoughts on that?
I'm curious if folks who are using different simulations find anything different. We don't need to make this like a fire-specific discussion section.
We have a slight bias and who got invited.
I think there are papers on this trend addressing the turnover or bend in the star-forming main sequence and showing that that's coincident at recent times with predicted development of a virialized halo. So there's some evidence there, not actual quenching, but a decline in star formation rate could be associated with the recent virialization.
So I'll throw it. It occurs to me there's actually the problem is a little worse, because halo quenching doesn't solve the problem of how you get rid of most of the metals, right? And it can't be the case that, right, most of the oxygen that the Milky Way is ever going to make, it made in the thin disk era. But most of those oxygen atoms don't live in the disk now. So you have to at least have a way of losing most of the oxygen atoms, and that can't just be halo quenching, because those have to actually come out of the disk.
I was wondering whether the simulations differ in the way they treat the recycled gas, like fountains or whatever. Certainly, if you have a huge blast, that spits it all over the place. It's quite different than, sort of small stuff that's being shot up and it waits a little bit of time and goes to the outer part of the disk. I think the distribution would always be within a given mass, within a given halo, and different structures may be included to the relative amounts of burstiness to quietness. The outer parts of the galaxy, the disk galaxy, have to reflect something about the history.
Unfortunately, that's probably like the absolute worst resolved part of the simulations, because, right, that's metal mixing out in the halo, and that's, no one believes that. Even the people who run the simulations don't believe that.
Yeah, so if you look at the metallicity in fire, for sub-Milky Ways, I think it looks reasonable. Then once you go to Milky Way, it starts to get high. And then if you just get a bit higher, then it just goes further up. So clearly, I think at about Milky Ways where this model stops working, and maybe it's agent feedback, it needs to blow out some of the metals, but at least there's some additional mechanism that's not included in the fiducial of a fire model.
Should we move on?
Yeah, so the third question, so we can constrain the Milky Way disk formation history by combining kinematics from Gaia with abundances. Is it possible to do analogous constraints, even if they have larger uncertainties, using stellar kinematic and chemical data in extragalactic systems? And if so, can we say something about how typical or atypical the Milky Way disk formation history is, either from this or more generally from this simulation?
This is something we're doing right now, but the problem is that you can only do this with the very nearby galaxies, and I think some attempts have been done with the gigantic cloud, and so it's something different we're doing right now.
Yeah, going back to the comments earlier made about looking for signatures in the circumgalactic medium, it would be great to have some quantitative predictions as far as how various column densities and especially kinematics of the key ions that we can observe from these same simulations with different histories.
Agreed. Thank you. So going back to this question of, this is just because I don't know about this, but how typical or atypical is the Milky Way's disk formation history compared to other galaxies? Do we know this, even just from the simulations?
Yeah, so in simulations, it looks like Milky Way is unusual, but not super uncommon. So if it also depends on how exactly star formation feedback models. But if we look at something like cosmological volume simulation like TNG, they are roughly 10% of Milky Way mass disk galaxies at redshift 0 have assembly histories or disk formation time similar to the Milky Way. So it's like within 2 sigma, not even an outlier, but also not a typical galaxy. And some people are trying to do similar measurements for Andromeda. So and I'm not sure if there are results already on this, but if they find that Andromeda also forms early, then this is interesting.
Yeah, I guess what I was trying to get at is things like, the diagrams that we saw in the last 2 talks of, metallicity, spin versus metallicity. obviously you're not going to get Gaia data extragalactically, but is there some diagram you can make that's vaguely like that, that is makeable for extragalactic systems, and where you could say, does the Milky Way look weird? You know, is the Milky Way, you know, slightly weird but not super weird, or is it super weird, or is it totally normal? Yeah, so Andromeda, you could sort of do something similar. That's a good. That I did not know that. I've learned something. But all right, how about beyond Andromeda? Is it totally hopeless? I'm looking at the observers. Yeah, for those who couldn't hear, the question was, okay, what would it take?
Yeah, I guess this is a question for the observers. So the plots that we've been showing, like these 2D histograms, have JZ by JC on the vertical axis, which I guess you can't, because we have the Milky Way being an ideal near-field laboratory with Gaia data. Things like that are very hard to produce in other, from extragalactic observations. So, what other parameters exist to measure rotation and angular momentum support outside of our own galaxy? One idea I had is to just, V phi, and if you could measure V phi as a function of radius in an extragalactic system, and then determine the metallicity of stars within those radius, you could produce something sort of similar. But again, I don't know how to how observers do that.
I'm a very old observer, so I can tell you that we try to simplify things. So for example, you're talking about phase 1, phase 2, phase 3. I would say, gosh, a simple experiment locally would be to take all the galaxies and relatively edge on this thick disk component. That's what you guys would consider to be phase 2. You certainly measure as a function of radius what the metals are. I mean, spectroscopy is not easy in my era, but today it's easy to think for young folks. They can study as a function of radius, as a function of height of the things that you're studying phase 2. And so to the extent that you can mock your simulations to today to see what the consequences for different kinds of histories, I think we can relate that. So that's phase 2. Phase 1 obviously is just thin disk portion, and the other part is material. So if you simplify the problem to location, I think us observers have a decent chance for extragalactic systems outside the local group. Other observers can contest that.
Just to say that the feature you're seeing is in the simulations is so, and in the Milky Way, is so dramatic that even if you have a cruder metric in other galaxies, it seems like something ought to be detectable. So one of the things you can do with observations is if you do a complete dynamical Schwarzschild model of a galaxy, particularly if it's edge on, you can back out the J distribution like you're showing, not in quite as much detail, but you can measure that. It's all, there's a lot of constraints, and so it could help if you could make some predictions from simulations of, say, what the different abundances look like in the different components in an edge-on disky galaxy, what the kinematics look like as a function of metallicity, et cetera, in sort of a 2D map, and give some senses that's something you could measure with observations.
I think we're getting better at isolating the major numbers that you would need in order to match up galaxies at different inclinations. And if you could do that and get face-on kinematics at high resolution, and then versus rotation curves and edge-on kinematics for the equivalent galaxies, it would be very helpful if you could, in your mocking, show us whether or not these different components, how do they show up kinematically? Do we see two different Gaussians of different width for a thick disk and a thin disk, and what's the amplitude of those various components? What would it take actually signal to noise to decompose?
people want another question or they want lunch? I think people want lunch. we won't talk about non-elusive gradients. That was our last question, but over lunch you can discuss non-elusive gradients.
Okay, so we do have lunch out there.